So my name is Niko Neufeld. I'm a CERN staff scientist, and I'm responsible for the IT infrastructure of one of the large experiments at the Large Hadron Collider. Okay, there are two ways to look at it. So there's the amount of raw data we produce. That's really data which is produced by the sensors, and this is a truly staggering amount. So we have a collision in the collider every 25 nanoseconds, so 40 million times per second. And we have several millions of sensors. So if you do the math, the raw data is several hundred terabits per second. Now, this is not all put into computers. So this is pre-processed with ASICs, FPGAs directly on the detector and reduced, significantly reduced. And then what we ultimately feed into computers is roughly nowadays, in this generation of experiments, roughly 100 gigabytes per second. It's still a lot. That still needs to be filtered down because this is still too much to store for posterity. And we filter that down, these roughly 100 gigabytes per second are filtered down to between 1 and 2 gigabytes per second. And that's then really kept on mass storage. And this is what the physics publications are based on. That's done on-site and is done on large server farms, which are also still on premises, close to the respective detectors, yes. So the data is then moved to the grid, as we call it, which is a kind of predecessor technology to clouds. It's essentially a federation of clouds, where we federate several scientifically public clouds which are operated by scientific institutions are federated into a common infrastructure for authentication and resource sharing. And that's where the actual data analysis is then done. So the physicists who do the analysis, that's not me, but my colleagues, they pull the data from there and then they do their analysis and then use this data to produce the actual publications. There's always a need for more processing. It is insatiable. You cannot match that because you can always do more sophisticated processing because there's really a data reduction on the way. So you have to throw away a lot of data, and whenever you throw away data, there's a strong worry that this would be the wrong data. If you only you could look a bit deeper. No? So there's always a need for more infrastructure. Also more clever algorithms. Sometimes algorithms are more clever by being faster, so this allows you to do more, but sometimes they look deeper into the physics and they need simply more resources to be able to run. So there's a bit of tendency you make a bit of compromise. Sometimes you as much as you can, you say, okay, fine, we can't maybe do the processing now live, or what we call online, so as the data is in flight. So we try to store more data, but that of course also has resource limits, so that we can afterwards come back to it. Because once it's on mass storage, and we still use a lot of tape, you can, if you have a clever idea afterwards or more resources, you can come back to it. So there's a bit of a tension to get some resources into mass storage and some resources to do more processing in flight. Everything is stored, yes. So what is stored normally is kept forever, because this the idea is that there's a lot of money was invested in getting it. So this needs to be stored, and actually there's a lot of effort in what we call data preservation, which aims at keeping this accessible, not only the data themselves, but also the programs and the software which was necessary to actually make sense out of these data. So machine learning is used usually in the last stages of the processing. There is now, with all this machine learning boom, there's certainly a lot of attempts to bring machine learning closer to what we call the raw data, so closer to the sensor data. So throwing completely unstructured sensor data at a machine learning has so far not been proven to be very efficient, but that's a very active area of research. So usually what one does is one already uses more conventional algorithms to create more abstract quantities. So normally what you see in the detector, what you measure the raw data, is actually charge deposits, stuff like that. So this is pretty raw. And then out of this you create kind of abstractions like a trajectory in a detector or an energy deposit. And so those can actually be presented to a machine learning system, and with quite some success in many cases. So it's usually you first have to create some bit more. It's a bit like the data preparation in classical machine learning terms. So you have to do some data preparation before you can successfully apply machine learning. But yes, machine learning in the higher levels is used. We tended to have a lot of innovation in IT. We have been overtaking the sheer size of IT infrastructure by hyperscalers, but we still, in terms of scientific compute, we are still one of the largest players. And so we try nowadays much more than in the past with commodity solutions too, because in the end the IT for us is not exciting as it is not the core business. So this is something which should serve the basic science we are doing. So we try to make the most out of the money the funding agencies generally give us to get the maximum amount of physics result out of the data. So that is still done, but only for chips which actually are directly on the detector, because those chips have what we call an analog front end, because they actually have to read the sensors, and this is not a digital process, so there is no off-the-shelf chip which will do that for you. But that's the only area where this is still justified, the enormous upfront cost. Otherwise, for any kind of digital processing, FPGAs are much more efficient, or ASICs if it's justified. So we use a lot of Xilinx in there. We also use in some places radiation tolerant chips, like from Actel, because in the LHC there's, during operation close to the detector is a fair amount of short-lived radiation, so we have to be radiation tolerant there. So there's a bit of compromise. When you are very close to the actual collisions, there you actually need radiation-hard ASIC designs. So that's also one area where still custom ASIC design is being done. Those cannot be changed easily, so the changing of these chips follows the upgrade cycle of the entire accelerator, which is usually a kind of 3 to 4 year period where we try to collect as many data as possible. And then both the accelerator and the experiment detectors undergo an upgrade cycle. The next one is starting actually now. End of this year, we'll shut down for 2 years, and there will be major upgrades in all the detectors and also in the accelerator. Typically, broadly speaking, it's a factor 10 usually to make it worthwhile to run for another 3-4 years. Very broadly speaking. So in the case of the experiment I'm responsible for the data acquisition of, we go from about, for example, just from the data we take off the detector, we go from about 50 to 60 gigabyte per second to about 4 terabytes per second. Okay? That's made possible by all this progress in particular also in network technology, and so makes it possible to fit this within still kind of an acceptable budget. It's at least a factor 10, up 10 to 20, depending where you look. Yeah. So we produce integrated, I don't know the exact numbers, but we integrate close to 20 petabytes per year are stored for indefinitely, let's say. And that is also going up. Of course, this is an integral, and this goes up, of course. Yeah. So supercomputers are being used when we get compute resources sort of offered, then we can efficiently use supercomputing resources. We use them typically more for simulation, because you need a lot of also simulated experiments to compare against the actual, because the physical theories which you get from a theoretical physics paper cannot be directly compared what you see in a detector. So you need a simulation of the detector response to underlying physics, and that is done very efficiently also on supercomputers. Yes, we work very closely with the European science networks and also with the US science networks. That's part of what our grid infrastructure allows us, is the software on top of these infrastructures. And network is certainly an important issue. And we try to be intelligent to place the data where the compute will be, or to use less data intensive on sites, for example, where data access is expensive, you run more CPU intense jobs and vice versa. We try to work. And since we have such a large amount of compute overall to do, we have enough sort of wiggle room to optimize this to an extent. So we have this aspect of the near source computing. There we are really hoping more for advances in heterogeneous compute. So we are looking into FPGAs also for compute, or GPUs for compute acceleration. So that's where we have this high throughput problem. Because to bring this data far away, because the rates are so enormous, this seems to be very costly, at least in the foreseeable midterm future. So to bring that all off-site. So there we hope that we get better computer technologies, also algorithms of course, to reduce the data on-site efficiently. And on the more sort of long-term side, Yes, I think all these things will help. I mean, supercomputers are an interesting resource when one can access to them. Our problems, because of the high collision rate in the accelerators, are embarrassingly parallel to begin with. So we do not need so much the low latency, high-speed connectivity, which is characteristic of a supercomputer, because in fact it's many sort of medium-sized problems, not one hard, large partial differential equation. But of course, the compute cycles on a supercomputer are very, very useful for us too. Why I get how much discount is difficult for me to judge. Definitely what I feel when I work with commercial partners, and I work a lot with many commercial, also large and smaller companies, is there's a lot of enthusiasm, a lot of goodwill. We get probably much more easily than we would get on our commercial interest. We get access to engineering resources, which we probably, in particular from large corporations like Intel, IBM, would not get purely based on the orders they get from us. So that clearly there's a lot of enthusiasm on the part of our commercial partners, which is very much appreciated. So events like this are a very efficient way of engaging, meeting a lot of, already existing or new potential industry partners. So that's why I go to events, this is the first time here for me, but I go to events also like supercomputing or ISC and DCD, because it allows me to see a bit how the market is evolving. It's very interesting for me, even though it's not always directly applicable, to see what commercial data centers are doing, what are the trends in industry, because since we want to follow, of course, this trend, so this is a very good way to see a lot of industrial development in one spot rather than traveling Europe, which would be a bit distracting. So definitely these events are very, very valuable for us to see on one spot where the industry is and what are the trends in industry.